So I had a look at the things that you're going through in this course to see like exactly how can I put in and connect to everything you've done before. And as what I realized, and as you probably also realized, is that thermal physics is a course with very many parts and subjects, and like different concepts coming in, and there's like a free energy here, statistics there, Gibbs and everything, and it's very easy to get confused. And so I thought that it doesn't hurt for me to repeat some of the stuff that you might have gone through earlier. And I also want to say that like if you feel stressed that this course is hard to wrap your heads around, then don't worry. It's completely natural to feel a bit overwhelmed by all the concepts and things that we're talking about. I want to just start with this figure. I'm going to go like to this introduction very quickly. So the point of this is to talk a bit about energy and momentum in particular. So if you were a physicist prior to the 1800s, you might envision that you're going through this, you're doing also these like collisions with billiard boards. Newton has derived his laws and everything. And then you look at this sort of situation where you have like two lumps of something colliding and then connecting. There are different things you can calculate based on that. So one thing you can calculate is the momentum, right, before and after. And what you will find is that the momentum is conserved, right? If you calculate it on this side and that side, you get the same thing, which is why people knew about conservation of momentum long before they knew about conservation of energy. Because it's not obvious from this here that there is like a quantity you can construct which is conserved. And it's not even conserved, right? Because this is an inelastic collision. It's only today that we know that the extra energy has gone into heating the molecules in this sample here. And the sort of drive to understand the energy and entropy concept came from the innovations in the 1800s, where they were trying to understand how can you make heat engines more effective. Essentially, they discovered coal, right, that you can burn coal and release a lot of energy. They put that into a chamber, burned it, and then they got gas to drive like a turbine. And then they were happy, but of course in France, where the amount of coal was not as abundant as in England, they were like, is there not a way we can do this where we can make it more efficient, right? Because burning lots and lots of coal to drive an engine is not very efficient. Is there a way we can construct our engine to make it more efficient? And that drove some people, among other Carnot, who was a French guy, to understand, sort of make the first grasp of what became entropy. Essentially, it has to do with how to make engines more efficient. Yeah, and just to emphasize this, I like this quote. It's a funny subject. The first time you go through it, you don't understand it. The second time you go through it, you think you understand it, except for 1 or 2 points. And the third time, you know you don't understand it, but at that time you're so used to the subject, it doesn't bother you anymore. And so I don't know where you are in this journey that Sommerfeld describes, but I think many people will sympathize. So the plan for today is the following. I'm going to take you, well, I'm going to very quickly repeat the 2 laws of thermal physics because we're going to use them later. Then some properties of gases, which is going to be important to study how an engine actually works. Then we're going to look at the processes, or just like a list of them. And then we're going to see how those processes are used to create a heat engine. And then we're going to flip the heat engine on its head and explain how that results in refrigerators. Okay, so the first law of thermal physics is that energy is conserved. So if I have a system and I add heat to it and do work on it, the internal energy of that system is going to increase by that amount. So I like to visualize this as follows. So the system here is this box, and on the system you can either add heat by heating it, or you can remove heat by having it release heat into the surrounding, at which point dq will be negative. You can have the system do work for you, in which case dV will be negative. You can do work on the system, in which case it will be positive, and you can not do anything. So my first task for you to just discuss for 30 seconds, try to come up with examples of things that fit into these boxes. Go ahead. Okay, I like it. These are my examples. I mean, yeah, adiabatic is something that typically goes very fast, so you don't get the chance to exchange heat. Adynamic is not as used, but you can see some results here. I'm doing work on. Do you have a question or no? Okay. Okay. So here I'm doing the reason that I bring this up is because when. Like the moment you start trying to do calculations on like how a heat engine works, you have to be really precise in, are you doing work on the system or is the system doing work on you? So that is the difference, right? The dV is positive, I'm doing work on the system. dV is negative, the system is doing work on me or on the surroundings. That's the main takeaway from this. And so the first law is that whatever you're doing here, it's going to change the internal energy of the system. And we know this as the law of conservation of energy. And the consequence of this for a heat engine, yeah, so sorry, these slides were originally Norwegian. I've translated them to English, but some Norwegian is like left in some of the figures. But drømmemotor means dream engine, right? So in principle, you could say, okay, maybe we can have like a dream engine. And the dream engine works like this. We're adding an amount of heat to the dream engine, and all of that heat is then removed as useful work. Useful work means that the system is doing work on us, meaning we can have it do something for us. It can push a rock up a hill, for instance, if you are interested in that. That's what we mean by useful work. And then the efficiency of this dream engine, it would be the amount of work that we get out of the system. Remember, it's minus because the system is doing work on us, divided by the heat that we put in. And this engine has an efficiency of 1, right? And since energy is conserved, we can never have a dream engine with efficiency greater than 1, right? Because of conservation of energy. So a consequence of the first law is that the efficiency has to be smaller than 1. Now, here's a task for you to quickly do. Let's say a coal-fired power plant in India burns 200 kilograms of coal every second. It supplies electricity with an output of 200 megawatts. When coal burns, it releases this amount of heat. What is the efficiency of this coal power plant? I'll give you 30 seconds to solve this exercise. All right. Since we only have 2 hours together, I'm not going to give you a day, but hopefully you've started solving the exercise, so you're not going to be too surprised when I get into this. So essentially what we have here is a system where I am adding coal, right? Every second I'm adding 260. I'm converting that coal to heat energy, and then I'm adding that heat to my engine, right? This is an engine. And out of that engine comes 2,000 megawatts, which is the work that I'm getting out of the power plant, which will drive my car or whatever else it's going to do for me. And so to calculate the efficiency, during 1 second, the amount of heat that is released is that 260 kilograms times the latent heat of the coal. So 260 times 23.9 megajoules, which turns into 6,211 megajoules. The work that this engine is doing for me is 2,000 megajoules. Remember, it's negative because this number is what's coming out of the power plant. And so this is just a figure of how it looks. There is 6,214 megajoules coming in, 2,000 coming out in terms of useful work, which means that the efficiency is 0.32. Most notably, less than 1, right? Which is no surprise because we believe the first law of thermal physics. So this is the point of a heat engine. Burn things, get work. But, okay, so we discovered that the limit is 0.32, not 1, right? So there should be a way to increase this efficiency. So is there a more fundamental limit on how efficient an engine can be? And for that, to answer that, we have the second law of thermodynamics, which you know as the total amount of entropy always being greater than or equal to 0. So here is my task for you. So whenever you're adding entropy to a system by adding heat to it, so if I add heat to an ice cube, for instance, then the entropy of that ice cube will increase by the amount of heat that I add divided by the temperature of that ice cube. So now I have an ice cube here of 1 kilogram, so it's a big ice cube, it's like this. It's at 0 degrees Celsius, and here I have a huge lake. This is like a 3D image of a lake. Do you see the lake? Yeah. I add the ice cube in the lake. When the ice cube melts, it requires 334 kilojoules per kilogram, and the heat capacity of the water is 4.2 kilojoules per kilogram Kelvin. When the ice cube melts, my question is, what is the change in entropy of the ice, and what is the change of entropy in the lake? And if you are able to do this quickly, then you can do step 2. When the ice is melted and the ice water heats to 20 degrees, what is the change in entropy of the water, and what is the change of energy of the lake? So this is ice water. It means the water that came from the ice cube. All right, try to solve step number 1. So, how do we do this? So this is the formula, right? It tells us if I add some heat to the system and divide by the temperature of that system, then the entropy of that system is going to change by this amount. So essentially, when the ice cube is in the lake, it's going to receive heat energy from the lake, right? Which means that for the ice cube, dq is positive. While it's melting, the temperature is always 0. And so I can calculate just by saying, like, how much heat energy do I need to melt the cube, divide by the temperature of the cube, and that will tell me how much the entropy has changed of the cube. And for the lake, I can say that, okay, but the lake is so much bigger than the ice cube, so it's not going to change its temperature a lot during that melting process. So its temperature will also be constant. So I can just take the same amount of heat that it lost and say that that was the energy that was taken from it. Use the same equation only with a different temperature to see how the entropy has changed in the lake. And when you do that, you get these two calculations. So so here we have this is the change of the ice. I take the amount of heat needed to melt the cube, which is this latent heat divided by the temperature of the cube. It should say Kelvin here. And I get 1,223 joules per Kelvin. I take the amount of heat that was added to the lake, which is negative, because it was taken from the lake, divide by the temperature, which is 293 kelvins, because it was 20 degrees, and it has a minus sign. So the entropy of the lake has decreased by 1,139 joule per Kelvin. And now we're gonna ignore this second calculation. It's not important for these purposes. But most importantly, the thing to notice here is that the entropy of the ice cube has increased by 1,200, whereas the entropy of the lake has decreased by only 1,100. Meaning there is a net increase of entropy in the universe of 100 joules per Kelvin. And that is the second law. Every time there's a heat exchange or energy exchange, if you sum off all the elements involved in the process, you're always going to find that the total amount of entropy increases. Yes. If the temperature is 0 Kelvin, then the entropy will be infinite. The entropy change, if you add like a joule of energy to something that is 0 Kelvin, then the entropy increase will be infinite. Of course, real systems with 0 temperature doesn't exist. And if it did exist, the moment you had added like a very small amount of heat to it, it would increase its temperature. And so you have to do a more complicated calculation, which is happening here, right? Because when the ice cube is heating up to the temperature of the water, then the temperature is constantly changing, and therefore you cannot use the simpler equation here. You have to do an integral instead. But it's doable. Yeah. Okay, so now the question is like, given this, what is the consequence for an actual heat engine, right? And the point is this. This is how an actual heat engine could look like. It takes some energy, some heat energy, from what we call a hot reservoir, and it puts that energy into it. You're pouring the energy into it. Like imagine the power plant in India, burning the coal, adding heat to that power plant. Some of that energy is transmitted as useful work, electricity in that sense, and some of it is released into a place with a lower temperature, TL, right? Minus dQL is going into that. And now we have two laws. We have the first law, which is that the energy that we add to the system, that is dQH, has to equal the energy that comes out of the engine, minus dQL minus dW. And we have the second law of thermodynamics, which says that the total amount of entropy, which is the change in entropy here and entropy here, has to be greater than or equal to 0. And we have an expression for the efficiency of this engine. And so what I would like you to do now is take this equation, solve for dQL, should be fast, then use the second equation to find a limit for the, sorry, this is not English. I want you to find the limit for the efficiency of an engine given these two equations. You have 30 seconds. Go. The solution is this, right? So I put it in, I rearranged my symbols, and then you get that the efficiency of TF2 is equal of this law here is 1 minus TL divided by TH. So the hotter the fuel burns, the more efficient the engine can be. The colder the reservoir, the higher the efficiency can be. And to relate this back to your question about the zero temperature thing, like if you look at this, if you imagine you had a reservoir which was 0 temperature, you could get the dream engine that I was talking about previously, because then the efficiency could go to 100%. Okay. All right, and so I'm just going to go through this quickly. Let's say that a locomotive has a temperature inside the engine of 500 degrees. Outside, it's 25 degrees, so it's a warm day. What is the best efficiency the locomotive can have? And to do that, I must recognize that, okay, there are two temperatures here. It's the hot reservoir, 500 Celsius. I need to convert to Kelvin. And I need to divide by, I need to find the low temperature. What is the best power? I insert into my equation 1 minus TL divided by TH. Low is 25 plus 273, that's 298. High is 500 plus 273, that's this, gives you 0.62. That is the most efficient that locomotive can be in that circumstance. If it's colder, the engine is more efficient. Can be. In principle, real engines are not as efficient, obviously, but this is the theoretical limit based on the two laws of thermodynamics. Okay. Point is, laws of thermodynamics determine how efficient heat engines can be. And in particular, the second law gives you an upper limit. Now, the way that heat engines actually work is by exploiting the properties of gases, the way that they expand and absorb heat when you experiment with them. And so to understand how to create an engine which creates work, we have to go through some of the properties of these gases. And then we're going to look at the processes that they go through and see how we can use that for engines and refrigerators. So, when you have I'm sorry for the bad drawing here, but this is my drawing. So here you have a gas, and inside the gas there is a pressure which is constantly pushing on the walls in all directions. And the force that the gas is pushing in total is equal to the pressure times the area of the box. That's going to be like that's going to be the force that it's pushing with. And so if you imagine, and here I have this is like a rotating wheel. So I'm trying to extract work from this gas expanding. And so when the gas is expanding by an amount dx, then the force pushing on this area here is PA times dx, right? But the area times dx, that is just the change in volume of the gas. So it's the same as dV, which means that the work that the gas is doing on the environment is equal to pressure times dA, PdV here. Which is why the work that the gas is doing on the environment is minus PdV, because dV is the work that we are doing to the gas. So if the gas is actually expanding, if dV is positive, it means that the work is negative, which is why we have this negative sign here. And so therefore, we can reformulate the first law of, or the second law of, we can reformulate the first law of thermodynamics in terms of these two quantities. The change in energy is equal to the heat that we add to the system, that's TdS, plus the work that we do on the system, that's minus PdV, and that will cause a change in the internal energy of the system. This equation is so important that you should tattoo it on your body, which I don't think counts as cheating, does it? No, it doesn't. So there you go. Okay, so properties of gases. You know this one. PV is equal to NKT if you're a physicist, nRT if you're a chemist, where P is the pressure, V is the volume, NKT. The condition for this equation to apply, this is the ideal gas law, is that the gas is ideal. And what does it mean for the gas to be ideal? It means that the particles in the gas are essentially moving around as ghosts, that is, not interacting, right? So when you're saying, I assume the gas is ideal, what you're saying is that you're assuming the particles are as ghosts, just moving through each other, not interacting with each other. We have the equipartition theorem, which says that in general, all of this is to give you some equations that we can use when we study the processes of gases, right? So there are a lot of equations here. I am not exactly sure which ones you have like intimate knowledge with, but I'm going to go through them and I'm going to restate them later on. But essentially, if you have a gas with n molecules, where each molecule has f quadratic degrees of freedom, the energy is given by U f half nkt, which in the case of an ideal monoatomic gas, which has 3 degrees of freedom, gives you 3/2 nkt, which is the one that you probably have used a lot of times. But this is the general one. Okay. Heat capacity is also important to understand how an engine works. So the heat capacity of a gas is the amount of heat that you need to add to it to increase the temperature by 1 Kelvin. Now, there are different ways you can add heat, right? I could have a box, keep the volume constant, and add heat to it. Or I could put the gas in a balloon and add heat to it, in which case the balloon is going to expand, right? Different processes, which means that the question, how much does the temperature rise if I add one heat, has to depend on the situation I'm adding the heat to the gas. And therefore, we operate with different heat capacities, one which is at constant pressure, that's the balloon example, and one which is at constant volume, that's the rigid box example. And my question to you, given this, which is greater, CP or CV? All right, show of hands. Who thinks you have to decide, you have to make one. If you're unsure, you have to decide which one you believe the most and make a decision. It's like the election. You have to make a decision, even though you're unsure. So, which one is greater? Who thinks that CV is greater? Show of hands. Couple, 3, 4 people. Who thinks CP is bigger? Many of you. All right. What is the argument? Does anyone want to explain why is CP bigger? Exactly. You add energy. Yeah, some of it goes to increasing the temperature. That's du. But some of it also goes to do work on the environment, which is so you have to spend more energy, more heat to get the same level of temperature increase. Good. That means that you understand this. And so here are all the equations. And it's a perfect place to take a break. So during the break for 15 minutes, I would like you to memorize as many of these equations as possible. So here is the laws of thermal physics, right? So now we're here. And so the point here is that we started with the laws of thermodynamics, saw how those lead to limits on how efficient an engine can be. Then we looked at the properties of gases, which are going to play into how we can manipulate these gases to extract work. And that is going to give us a recipe for how a heat engine can be made. So this is what's called an Otto engine. And what you have on the right here is called a PV diagram. PV diagram, it can be used for many things. It can be used to plot a phase diagram of different substances, right? What is the phase of this? What is ice? What is H2O at this temperature and this pressure? But in the case of a heat engine, we're just assuming that this is all gas, right? And then we're looking at the changes that a gas goes through as we are doing something to it, right? So we start here, 1. And we keep the volume constant, but we increase the pressure. What are we doing to the gas? Yes, here. Sorry? It's isochoric, but physically, what are we doing to it? It's isochoric because the volume is constant, yes, but what are we doing? Why are we warming it? How do you know? Exactly, right. Temperatures. Different temperatures are all on this line here. So all the points on this line have the same temperature. All the points on this line have the same temperature, which means that the temperature is rising, which is the only way to get if it's the same volume, the only way to get the pressure up is by adding heat to it. So from 1 to 2, we're adding heat to the engine. From 2 to 3, what are we doing to the gas? We're letting it expand, yes? Are we adding heat to it? Since we're letting it do work and the temperature is constant, we have to be adding heat to it. Does everyone agree? Do you agree? The temperature is the same for the entire thing, yes. Then you agree. Right, perfect, right? So, like, the direction here is always telling us something about what are we doing to the gas. And then we can derive all kinds of different equations to describe the initial and the end state of the gas in the different situations. But I want you to whenever you're seeing these things, try to like analyze each step. What is happening to the gas we're taking? Are we adding heat? Are we adding work? Are we getting work, or are we getting heat? So this was an isochoric process, right? So it means a process in which we're adding heat to the system, but the volume stays the same. So a couple of different things are happening. The temperature is increasing, right? If you imagine the particles moving around in the gas, then we're essentially adding heat here, and the particles are increasing in their speed, which increases the temperature. It also increases the pressure. It also increases the internal energy, and we're adding more heat. No work is done by the system. I'm going to show you a lot of these plots now very quickly. But you're going to get the slides afterwards. You can have a look at the things if you'd like to check them more carefully. The point is the constant volume. So here are the equations. You can derive them, and you should. So for all of these equations that I'm showing you now, you should be able to derive all of them based on like just the notion of an isochoric process. Now I'll go through this one more slowly, just so you can get the idea, and then I'm going to go faster through the other ones. But here's the point. The gas is starting at this state, volume 1, P1, and I'm adding heat to it to get it to a state of P2, P1. The work done is the integral of the tiny works done at every step. And the work done is the pressure times the change in volume, but since there is no change in volume, the work done is 0. There are essentially no limits on this integral. The heat that I need to add is given by the heat capacity, because the heat capacity is how much energy I need to add to increase the temperature. So the heat added is the integral of CV dt. I'm using CV because it's constant volume, right? It's a constant, I assume. So it goes outside the integral, and then all that's left is the integral of dt, which is just the distance between the endpoints. And then this gives me this equation here once I insert the formula for the heat capacity of an ideal gas, or a gas fulfilling the equipartition theorem. And the change in energy is only due to the first law, just given by the heat that we add to the system, which is just this thing here. So here you can see how I derived all those equations. On the scale from thumbs down to thumbs up, how clear is this slide and the content? Mostly clear. Okay, good. So this you can do for all of the processes, right? So let's look at this one. This is an isobar process, meaning it's happening at constant pressure. We're adding heat to the system, and we're letting the system expand as a result, keeping the pressure constant at every time. So when I plot the pressure as a function of time, it doesn't change. But when but the temperature is increasing. That's not obvious, by the way, but that's what happens. And the internal energy is increasing. Those two are related. We're adding heat. We're getting work from the system. The work is negative, so we're getting work out of the system. And then I've plotted this mysterious quantity here, which I'm not going to go into in this presentation. But the point is, it's constant for some processes. Isobar. In a PV diagram, it looks like this. So we are going from a state of P1, V1, and we're adding heat to it. And at the same time, we're allowing it to do work on the environment, which means that it is doing work for us. So now we can calculate the work done. It's an integral dV. Insert the equation for dV. We get this formula here. Boom, there we have the equation for the work done. The heat that we add is now we have to use the heat capacity at constant pressure. We take it outside because it's constant, boom, done, boom, done. And now we have like an expression for the change in internal energy too, based on the first law of thermophysics. That's isobar. There are other processes. Oh yeah, I wanted you to calculate something, but I'm going to skip this now because you've done a lot of this from before. Isotherm means a process where the temperature is kept at a constant level. So the temperature is, we're adding heat to the gas, it's expanding, but at a perfect rate where the temperature is kept constant all the way through, right? So this is here, the pressure is decreasing, the internal energy is the same, we're adding heat and we're getting work. In a phase diagram, in a PV diagram, it looks like this. So these lines here are called isotherms. They are lines along which the temperature is the same. And so when the gas is expanding along this isotherm, it goes from P1V1 to P2V2, and the temperature is kept constant here at 60 Kelvin. And we can do the same thing. We can calculate what is the work done on the gas in this process. We can calculate the change in internal energy, and we can calculate the heat done, right? So these are all equations. Again, like these. And of course, here the problem gets more tricky because in order to calculate the work, now previously where we could just like pull out the P from the integral, we cannot do that anymore because now the pressure is changing as we're moving along the line. So we need to keep it. And then we get an integral which we need to solve, which gets like the logarithms and stuff. So that's why they come in here. Make sense? Nodding, right. And then the last one is adiabatic. So the adiabatic process is one where you're not adding any heat to the system, so you're just letting it expand or just contracting. For instance, if you're doing something very quickly, it's typically adiabatic because there's no time for the heat to go into the system. So you can see the energy goes down, we're not adding any heat, and the gas is doing work on the environment if it's expanding. Pressure is going down, temperature is going down. That's the adiabatic expansion. If you look at it from the point of view of the PV diagram, we see that we start here at the high temperature. The gas expands, and as it expands, it's sort of crossing these isotherms as it's expanding. So it's ending up on a lower isotherm than it was in the beginning. And in order to calculate the work and everything, we have to pull out our integral equations again. You can derive these equations. There's this gamma coming in here, and then there's like these two laws, which says that that the P times V to this gamma coefficient is constant for this process. The same too. This one is constant. All of these are things that you can derive based on the equations that we've seen so far. And I recommend that you try, because it's very helpful to feel like you're understanding all of these processes. That's the point. So, laws of thermodynamics gives limits on how efficient an engine can be. That's just like in the abstract. And then we have equations which describe how gases behave and how the gas properties change as the system is being compressed or we're giving heat to the system. So now the question is, how do we use these principles, these processes, to extract energy from a system if you add heat to it? So that's that's a heat engine. And I mean, we've seen one here, this one, the Otto engine. I'll probably start here. So what's happening here in this process? We already looked at this one. So here we're adding heat to the system. We discussed this. Here, the system is expanding while we are adding heat to it. So we're still adding heat to the system here and here. Only here we're getting some work out of the system. The system is doing work for us. Here, we're keeping the volume constant, so no work is being done, but the temperature is decreasing, which means that the system is giving off heat to somewhere in this process from 3 to 4. And then from 4 to 1, the system is contracting, meaning that we are actually doing work on the system, but not as much as we got out here. And at the same time, the system is giving off some of its energy. It's the exact opposite of this process here. So the point is, when you calculate all of these processes, the sum of it, like how much energy are we adding here, how much work is it doing here, how much energy are we getting here, etc., then you end up showing that you get some netto work out of it, and it has absorbed some heat, and it has released some heat, and you can do this calculation. Right. Repetition, yes. So this is the repetition. Remember, just as a consequence of thermal physics, we know that this is a limit for how efficient an engine can be. It doesn't have anything to do with gases. It's just a principle of thermodynamics. And here's our engine. Yes, okay, this is where I wanted to go, right. So from 1 to 2, no work, we're adding heat to it using using the formulas that we derived in the previous one. From 2 to 3, we're both getting work out of the system, and also we are adding heat to it. Those were the equations that were derived in the processes thing. Like, I want you to, even though you don't necessarily agree with these equations, I just want you to realize that like they come from analyzing each of these processes very carefully. That's where they're coming from. 3 to 4, the work done is 0 because it's isochoric. It's no change in volume. We're getting heat from it now, but the heat that we add is given by this here. Tc is the cold reservoir, the end temperature. TL, sorry, there's like a equation mix-match here. TL is Tc, Th is Th. Cold, low, yeah. And then in the last step, we are doing work on the system. So this one is actually positive. It's positive because of the. It doesn't really matter. It's going to end up being positive. Q is also negative. The system is expelling heat into some environment. So here's what you do to calculate the efficiency of an actual engine. You look at how much during this process, how much heat have we put into the system. Then we calculate how much work have we done on the system. And to do that, we need to calculate the situations where we were adding heat to the system. And the places where we're adding heat to the system was 1 to 2 and 2 to 3. And at 3 to 4 and 4 to 1, the system was giving off heat to the environment, which is why they're not included, because we're only interested in how much energy, how much work are we getting from the amount of heat that we're putting in. And then we calculate the work by summing the contributions at every step. And then we can insert all of our equations from all of the processes. And then you get something that looks like this. The details are not the important part. You have to work through them to understand them. But the point is to know where they came from. And if you take this equation, you see that you get the relation between V2 and V1. And if I plot this Stirling engine as a function of the ratio of V2 to V1 here, you see that if the So the point here, what is V2 and V1, right? So V2 and V1, those are the limits of the engine, right? So what's happening to this gas inside this engine is that it's kind of like it's V1, it's small. I'm adding heat to it. It's the system, the volume is the same. And from step 2 to 3, I'm still adding heat to it, but now I'm letting it expand, becoming bigger until it's like at V2. And then at some point at V2, I say like, okay, enough is enough. I'm done adding heat and getting work from you. So I stop, and then I let it cool down at the same temperature. So it's still the big one, still V2. And then I compress the gas in order to be able to restart the process at a lower temperature. So it requires me less work to compress the gas than the work that I got out. Essentially, that's the process. So V2 and V1 are the volume at this point where the gas is small, and the volume here when the gas has expanded. And the point is that this equation tells us that the efficiency of this engine depends on the ratio of the volume of the gas when it's big and the gas when it's small. And I can plot it so as a function of V2 divided by V1. So if the gas is twice as big as when it's twice as big as the initial gas, then the ideal then the efficiency is 0.3 or something. And then the theoretical limit given by the second law of thermodynamics is 1 minus Tc divided by Th. So in some sense, there are like 3 levels of reduction in idealism here, right? So you have the first law, which tells you that like you cannot have an efficiency which is larger than 1. Then you have the second law, which gives you another limit, cannot be greater than this. And then you have like a third limit. It's like, okay, but the gas is going through this process. What is the maximum that you can achieve in this case, which is even lower, right? As you see, like it cannot be bigger than this when you have an Otto engine. Right. So the Stirling engine, is it Stirling or is it Otto? Right, you're right. It's Stirling. It's Stirling because the Otto is just for visualization for processes, I think. So what is my point? Yes. Okay. So the question is there a process where the efficiency is actually the ideal one given by the second law of thermodynamics? And the answer is yes. And it's called the Carnot cycle. And the Carnot cycle looks like this. It's first an isotherm expansion to here. Then it's an adiabatic expansion to 3. Then it is an isotherm compression to 4. And then it's an adiabatic compression to 1. And if you take all the equations that we derived and you put them into this formula to calculate the ideal, the efficiency of the Carnot engine, you get the theoretical limit proposed by the second law of thermodynamics. Can we build the Carnot engine? The point is, I think the point is that like these adiabatic steps, like 2 to 3 and 4 to 1, those are quite easy. Those are quite easy. You can just like crunch it together really fast, and then you're there. But the problem is these isotherm ones, like expanding, like adding, like just adding just a little bit of heat every time so it expands but doesn't change the temperature. That is like the thing that has to go really slow if you want it to be perfectly well. Okay. So that's kind of heat engines. And again, the point is, I keep coming back to this, laws of thermodynamics put limits. First law puts a limit, second law puts a stronger limit. Then you have the properties of gases, which we need in order to construct an actual heat engine, which relies on these processes. And we use them to create heat engines. And this is a heat engine, right? This is what it does. It takes some heat from a hot reservoir, does some work, and then puts some of that heat into a cold reservoir, some extension. So my question now that I would like you to think about without discussing with each other for 10 seconds, just like inside your own minds, what happens if the energy in this diagram flows the other way? You do work to take heat from the cold environment and put it into the hot environment. Essentially, a refrigerator, right? Using energy to pull heat out of the fridge and out on the back of the refrigerator. Most importantly, the amount of heat that is going out is larger than the amount of heat that you're pulling out of the refrigerator, right? Which is why for your fridge, you're taking more, you're heating the environment more than you're cooling down the fridge. Which is why if it's really hot, then opening the refrigerator is not a good idea. Because then you are just spending more, you're just like increasing the temperature of the room. So, now you know. Right. So here is, so essentially a refrigerator is a heat engine in reverse. And the reason I have changed the signs of all of these things now is because now we're sort of looking at the reverse process. So now I'd like you to answer these questions together. In this figure, where do you store your food? Why have the signs switched? We define something called the coefficient of performance as dQL divided by dV. Why? Question, if a fridge removes 1 joule of heat from its interior but expels 3 joules of heat to exteriors, what is the coefficient of performance? And what is the maximal coefficient of performance possible according to the laws of thermodynamics? So I'll give you 3 minutes to answer these questions. All right, so in this figure, where do you store your food? Yes. Here. Does everyone agree? Nice, that's where you have your food. Excellent, then we know that. Why have the signs switched? I mean, to me, the short answer is because I changed the arrow I changed the direction of the arrows. I mean, this is always the thing. When you're doing these calculations, you have to be very careful. Like, what is positive here? Is it supposed to be positive or not? And you just have to like do it a lot to get the training. But that's why. Like, I changed the direction of the arrows. To me, it makes more sense to write this as minus dq because that is the amount of energy that's going out of the fridge. Because everything that is going into this thing here is positive. That's my convention. The coefficient is defined as this. Why? Perfect. And then you have this equation, or it removes 1 joule but expels 3 joules. What is the COP? Show me by fingers the COP. 0.5, 0.5. Oh, 1/2. I like it. Okay, I forgot. I thought it was going to be 2, but that's not the case, is it? No, because what you're saying is you remove 1 joule of heat, you expel 3, which means that you've used 2 joules to run the thing, and that gives a COP of 0.5. Good. Exactly. And then the last question, if you had time to do that, is, of course, this question of what is the maximal COP possible according to the laws of thermodynamics. And the way to calculate this is actually to do the same thing that you can do for the ideal engine, only now taking into account that this is the reverse operation, right? So you start by saying that the entropy change in the low temperature reservoir has to be is equal to this, right? It's actually going to change. So the entropy of the fridge is decreasing. And then the entropy in the hot reservoir is going to be minus dq over dh, which is positive because your dq is negative here. And then you use the first law to get the conservation of energy. You know that the entropy in the universe has to increase. That is, the entropy decrease in your fridge has to be counterbalanced by the entropy production in the environment. That's the second law. And you use those equations to solve for dQL divided by dV. And at the end, you get this equation here. Yes? Oh, yes, you're right. You're right. Yeah, exactly. It's an equal sign is the wrong way. Yes, good, well seen. It was a test to see if you're paying attention. What is the maximal COP for a typical fridge, and what is the actual COP of a typical fridge? Try to calculate those two things for me. 4 degrees Celsius here, 23 degrees here. 15. Okay? And it's correct. 15. Is it too high? What is the COP of an actual fridge? Don't know. Did anyone check? Did anyone Google? What is the COP of a real fridge. Does anyone know how much heat, if I add like a joule of energy to my fridge, how much heat can I pull out of the fridge, essentially what I'm asking. The answer is typical fridge are around 4 to 5. That's where we are. In other words, still away from like the ideal limit of an ideal fridge. In the same way that the heat engines are not as efficient as the ideal engine, the fridge is not as important is not as good as the ideal fridge. And in principle, you can use the Carnot, like if you use the Carnot cycle in reverse, you can use that to get an ideal fridge. You just go the other way in the diagram, and then you have a fridge. And I mean, this is the next to last slide. So to summarize the sort of story here for the 7th time, thermal physics gives us limitations on how efficient engines and stuff can be. And the two laws, we can use them to derive these limits. In order to do it in actuality, we have to use real things. Gases are the most accessible to us. They have certain properties, and when we put them through changes, these properties change, like you change when we put you through a course on thermal physics. They can expand and contract, and all of these we have equations for. We can use these equations to calculate the work done and the heat added during one of these processes, and we can calculate the efficiency of an engine. And that's something that you should be able to do in this course, like take like a process and calculate the efficiency of it. If you turn the heat engine in reverse, you get refrigerators, where the interesting quantity is not the efficiency, it's the coefficient of performance, which is defined slightly differently. But it's the same kind of thing as the efficiency, right? If an engine is very efficient, it means that the corresponding refrigerator is also has a high coefficient of performance. So that's sort of the idea of this whole story. Now, I think that thermal physics don't get the attention that it deserves in like a physics among physicists in general, and like very often like people will go out of the university and they like talk about like quantum physics, so how that's exciting, and like computation and stuff. But I mean, without these heat engines, we wouldn't have like the industrial revolution that sort of fuels everything. Like the only reason that we are sitting here like in warm buildings and have like all this technology is because we have been able to extract work from heat engines. So that was like during the 18th century, and these refrigerators, they weren't discovered until like the late 1800s, like bordering on like the start of the 1900s. And once you have a refrigerator, what can you do? You can cool food to preserve it, right? So that we can transport, we can keep food more available to more people. We can separate gases, because the way to separate oxygen, for instance, from the air is to cool it to the point where the oxygen liquefies, solidizes, right? That's not possible without these refrigerators. Vaccines are not possible without refrigerators. I mean, like this is, to me, like this thing here is like the second piece of the puzzle, which has allowed us to actually get like the high-tech world that we live in. And so whenever someone tries to like I don't know, like wash away the importance of thermal physics or like talk badly about thermal physics, I would like you to kick them. Did I say this was recorded? Yes, I did say this was recorded. that is my last, and thank you very much for your attention.